Hello, I am Dr. Pratula Nandadas of Jadavpur University. I am going to teach you the course Real Analysis and Measure Theory. So, let us first start the discussions on module 1 of chapter 1. In this module, we are going to introduce the notion of Lebesgue outer measure. Now, let us first try to understand what is the motivation behind the introduction of this concept. Recall that for two sets A and B of real numbers, a mapping f from A to B is called injective if f x is not equal to f y when x is not equal to y, that is distinct elements have distinct images. This implies that the number of elements in the set B should be greater or equal to the number of elements of the set A. If we consider a mapping f from the set A to the set B, the mapping is called surjective or onto if for any y belonging to the set B, there is a pre-image x belonging to the set A for which f x is equal to y. Existence of a surjective mapping implies that the number of elements in the set A is greater or equal to the number of elements in the set B. If the mapping f from a set A to a set B is both injective and surjective, it is called a bijective mapping, and this implies that the number of elements in both the sets A and B are equal, and we denote the number of elements in the set by the cardinality of the set. So, cardinality is a measure of the set which gives us the number of elements in a set. Now, consider two intervals, say open interval 0 1 and open interval say 2 to 5 on the real line. Now, we know that there is a bijection between these two intervals. In other words, the number of elements in both the intervals are same, but when we draw them on the real line, do they look same? Of course not, because when we draw them on the real line, there is another characteristic associated with the sets. Since these are intervals, so there is a notion of length associated with them. Open interval 0 1 has the length 1, whereas open interval 2 to 5 has length 3. So, though both the intervals have same number of points, that is both have same cardinality, but they have different lengths. In undergraduate syllabus, in undergraduate calculus, we use the notion of lengths of intervals both in differential calculus as well as in integral calculus, particularly when we define the Riemann integration. Now, the natural question is whether we can extend the notion of length from the collection of intervals to a larger class of subsets of real numbers. So, we want to know about this, and the notion of Lebesgue outer measure is the first step towards this direction. We start by defining the length of an interval. So, the length of a bounded interval I which may be open or closed or half open with endpoints A and B, where obviously A is less than B, is defined as the number B minus A, and we write L of I, length of I is equal to B minus A. The length of an unbounded interval I, that is an interval whose left end point is minus infinity or the right end point is infinity, is defined as the number infinity, and we generally write L of I equal to infinity. So, every interval on the real line has a number assigned to it. It may be a finite number or may be plus infinity. So, every interval has a length. Now, as we have said, what should be the length of an open set or a closed set? See that when we consider an open set of real numbers, we know that every set of real numbers which is open can be expressed as countable union of pairwise disjoint open intervals, which are called the component intervals of that open set. And consequently, it is very natural to define the length of an open set as the sum of the lengths of its component intervals of which it is composed of. See that since we have only countable number of open intervals, so we have a sequence of real numbers and we can add them with the help of the theory of infinite series, and the sum is also unique. If we consider a closed set, it is not that much obvious, but if we consider a bounded closed set, then the bounded closed set is always contained in some open interval. So, if I consider a bounded closed set capital F, where capital F is subset of open interval capital A capital B, we can define the length of F as B minus A minus length of O, where O is open interval capital A B minus F. See that O is an open set, so we already know its length. Now, if we consider a length like function which we will call as measure, we should first understand what should be its desired properties. That is, we should first understand what properties of the measure we are expecting. From the intuition of the length function, our expectation is that first mu should be non-negative, that is mu A should be greater than 0 for all A subset of R for which it is defined. Secondly, the set function mu should be monotone, that is, if A and B are two sets of real numbers whose Lebesgue measures are defined and A is subset of B, then we should have mu A less or equal to mu B. See that this is also very natural, because if I have two scales, say one is smaller than the other, then the length of the smaller scale is always less than the bigger scale. Thirdly, it is very obvious that since we are extending the length function into a measure for an interval I which already have a number, namely the length of the interval assigned to it, mu I should be equal to that particular number, that is the length of the interval. Fourthly, see that for a subset of R and y belonging to R, if we define a plus y as the collection of all points small a plus y, where small a belongs to capital A, that is the translation of the set A with respect to the number y, then mu of a plus y should be equal to mu of a, that is mu should be translation invariant. Again observe that this is also quite natural, because if I have an interval, say open interval a b, where a is less than b, then its length is b minus a, and if I translate it by a number y greater than 0, then I have the interval a plus y, b plus y. So, we are just shifting the interval on the right hand side, but the length of the interval does not change. 5. For two disjoint sets A and B of real numbers, we expect that the measure should have the property that mu of A union B should be equal to mu A plus mu B, because see if we have two disjoint intervals, say closed 0 1 open and closed 1 3 closed, then if we take the union of these two intervals, we have the interval closed 0 3 closed, and obviously the length of this interval is equal to 3, which is equal to 1 plus 2, that is the sum of the two intervals. More precisely, we expect that the measure mu should be countably additive. That is, if a n belonging to capital N is a sequence of pairwise disjoint sets of real numbers, then we should have mu of union n equal to 1 to infinity a n is equal to sigma n equal to 1 to infinity mu of a n. Obviously, for those sets a n for which the measure can be defined. Now, we start with the formal definition of Lebesgue outer measure of a set of real numbers. For any set A of real numbers, the Lebesgue outer measure of A is defined by mu star A equal to infimum of sigma n lin, where in is a countable collection of open intervals covering the set A. Why we take this definition? Because see that we already know from the theory of real analysis in undergraduate syllabus that the whole real line can be covered by countable number of open intervals. So, any of its subset can also be covered by a countable collection of open intervals, and each open interval has a length, and we can add these numbers, since all the numbers are non-negative, so this sum always exists and it is uniquely determined. We start with the basic properties of Lebesgue outer measure. First, see that from the definition of Lebesgue outer measure of mu star E, since we are taking the infimum of non-negative numbers, so the infimum should also be greater or equal to 0, and of course, it is less or equal to infinity, and this shows that mu star has the property that 0 less or equal to mu star E less or equal to infinity for any subset E of R, that is the Lebesgue outer measure mu star is non-negative. The second assertion is also very obvious, that mu star phi is equal to 0, since phi is contained in any open interval. The third assertion is that if we take two sets of real numbers A and B, where A is subset of B, then mu star A is less or equal to mu star B. This is also quite obvious, because if we take a cover of B by countable number of open intervals, then since A is subset of B, this countable collection of open intervals also covers the set A. Then the fourth property is that for any A subset of R and X belonging to R, mu star of A plus X should be equal to mu star of A. See that this is also quite natural, because if I have an interval say 0 1 on the real line, and if we translate it by a number x, then we get the interval x 1 plus x, and this is true for any interval with endpoints a b. So, already intervals have this particular property, that when we translate the interval by a number x, the length does not change, and the same is true for the Lebesgue outer measure also. The proof is not given in the slide presentation, but the proof is given in the course material. Finally, we have the property that for any interval I, mu star I should be equal to length of I, which is very natural, because we have extended the length function to the notion of Lebesgue outer measure, and we are going to prove this assertion in details in the slide presentation. So, we are going to prove that the Lebesgue outer measure of an interval is equal to its length. We start with a closed bounded interval I, say closed interval a b. So, we want to show that Lebesgue outer measure of I is equal to the number b minus a. Let epsilon greater than 0 be given. Now, see that we can write I equal to closed interval a b. This is subset of open interval a minus epsilon b plus epsilon. So, a minus epsilon b plus epsilon is an open interval containing closed interval a b, and from the definition of Lebesgue outer measure of I, it now readily follows that mu star of I should be less or equal to the length of this particular interval, which is the number b minus a plus 2 epsilon. But this is true for any epsilon greater than 0. So, we must have mu star of I less or equal to b minus a. So, we have one part of the equality. So, next we will have to show mu star I less or equal to b minus a. Now, before proceeding, let us consider the situation. We are considering the set closed interval a b. If we start with a countable collection I n of open intervals covering closed interval a b, we want to show that sigma L I n, where the summation is over n, this is greater or equal to b minus a. But we already know that closed interval a b has Heine-Borel property, that is any open cover of closed interval a b has a finite subcover. So, when we are starting with a collection of open intervals I n covering closed interval a b, there is a finite subcollection of that collection of open intervals which actually covers closed interval a b. So, it is sufficient to prove the result for a finite collection of intervals covering closed interval a b. So, we start with this assumption that we start with a finite collection I n of open intervals covering closed interval a b. We start with the left end point of the interval, that is a. Now, since the collection I n covers closed interval a b, so there must exist a member of this collection, say a1 b1, which contains the point a, that is a1 should be less than a less than b1. Now, see, there are two situations which can arise. If b1 is greater than b, then we have closed interval a b subset of open interval a1 b1, and obviously b minus a is less than b1 minus a1, and the proof is complete. If not, then b1 should be less or equal to b, but then we have b1 is a member of closed interval a b, and consequently, since I n covers closed interval a b, so there must exist another member, say open interval a 2 b 2 from this collection, which contains the number b1, that is a 2 less than b1 less than b2. Again, two situations can arise. If b2 is greater than b, by the same argument we have closed interval a b subset of open interval a1 b1 union open interval a2 b2, and the proof will be complete. Otherwise, the number b2 should be less or equal to b, and again I can get another member from the collection I n, say A3 B3 which contains the number B2. So, we can proceed in this way. Now, observe that we have only finite number of intervals in our hand, and if we proceed in this way, this process cannot go on infinitely. So, this process must stop at some stage. Suppose the process stops at the kth step, that is when we get an open interval ak bk. So, I have a collection of finite number of open intervals a1 b1, a2 b2, ak bk from the original collection in, where a1 should be less than a, b1 should be less than bk, and for each I we have this inequality a I plus 1 less than b I less than b I plus 1. Now, clearly, if we consider the sum of the lengths of the intervals in, this is greater or equal to sigma I is equal to 1 to k b I minus a I, and this is actually equal to b k minus a k plus b k minus 1 minus a k minus 1 plus dot 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 plus b 1 minus a 1, and we can rewrite the sum in this way: b k minus a k minus b k minus 1 minus a k minus 1 minus b k minus 2 minus dot 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 a 2 minus b 1 minus a 1. Now, observe that from the above relation between a I and b I, that is a I plus 1 less than b I less than b I plus 1, it immediately follows that each of the numbers a k minus b k minus 1, a k minus 1 minus b k minus 2, a 2 minus b 1, these are all negative numbers, and so the whole middle part of this expression is a positive number. So, clearly this is greater or equal to b k minus a 1, which is again greater or equal to b minus a, and this shows that sigma L I n is greater or equal to b minus a, and consequently we have the outer measure of I is also greater or equal to b minus a, and we have the result. So, what we were saying that we already have mu star I greater or equal to b minus a, and consequently we have mu star I is equal to b minus a. So, we have proved the result for a closed interval a b. Next, let I be a finite interval. Let epsilon greater than 0 be given. Now, see that within any interval with positive length, I can always insert a closed interval. So, choose a closed interval J subset of I such that L j is greater than L I minus epsilon. Then we get this relation that Li minus epsilon, this is less than Lj, but we have already seen that for a closed interval length is equal to the Lebesgue outer measure. So, Lj is equal to mu star j. Since mu star is monotone and j subset of I, so mu star j less or equal to mu star I, and I is again subset of I bar, where I bar stands for the closure of I. So, mu star I is less or equal to mu star I bar, but see that the closure of any interval is the corresponding closed interval. So, mu star I bar is equal to L of I bar. This is again equal to L of I, because we have defined the length of intervals in this particular way. The length of the interval does not change if we take the endpoints or delete the endpoints. Since this is true for any epsilon greater than 0, so we get L of I equal to mu upper star of I, that is for any finite interval. Now, we have the result that the Lebesgue outer measure of any finite interval is equal to its length. Finally, let us take an infinite interval I. Again, see that if I is an infinite interval, then either on the right hand side we have infinity, or on the left hand side we have minus infinity. Suppose it is of the form a infinity, where a is the left end point and infinity is the right end point. For any g greater than 0, we can find a closed interval delta subset of I with L of delta greater than g. Obviously, if we say take the infinite interval open a infinity, I can always consider the closed interval a plus 1, a plus g plus 2, and so I always have a closed interval delta subset of I with this particular property. Then mu star of I is greater or equal to mu star of delta, because I contains delta and mu star is monotone. And again by the first part, we already know that mu star of delta is equal to L of delta, which is greater than g. And this relation is true for any g greater than 0. So, we have mu star of I, a number which is greater than any positive real number. That is, we must have mu star of I equal to infinity equal to again length of I, and this completes the proof of our assertion. So, to summarize, what we did in module 1 of chapter 1 is that we have extended the length function from the class of intervals of real numbers to the collection of all subsets of real numbers by the notion of Lebesgue outer measure. We have seen that this function has nice properties because it has almost all the characteristics of the length function, in the sense that the Lebesgue outer measure is non-negative, monotone, it is countably sub-additive, as also it is translation invariant, and the nicest part is that we could define the Lebesgue outer measure for all subsets of real numbers, but we could not prove one property for the Lebesgue outer measure. We could not show that it is countably additive. With this comment, we end this module.